In today's video, I would like to introduce you a very nice problem of International Mathematical Olympiad competition. Here is the following setup. Let P1, P2, P3 and so on and so forth as an increasing sequence of the prime numbers for any integer n. Okay, so the question, we are going to prove this product P sub 1 through P sub n is inferior or equal to the 2 to the n. Okay, we have this component contain prime numbers P sub 1 through P sub n. Since this prime is dependent on the integer, so as you increase the prime number, this value is increasing as well. Okay, so I would be recommend to give the try to spam pre-regret into the solution. Go ahead, pause this video when we come back to see the full solution. Okay, now let's get started. The best way to prove this one, we are going to use induction hypothesis. Okay, but induction hypothesis is not enough to prove this one, so we are going to use arithmetic and number theory notions. I'm going to check the base case when we have n equals 1. We'll have P sub 1 is inferior or equal to 2 to the 2 to the 1, which is 4, which is 2 to the 2, 4. Since this sequence, which is on the right hand side of this inequality, is a power of 2, which means P sub 1 must be equal to 2. Okay, n equals 2. I'm going to check the second case. We have P sub 1 is multiplied by P sub 2 is inferior or equal to 2 to the 2 to the 2, like this. This one is giving us 2 to the 4. Okay, I'm going to replace P1 with its value. So I will have 2 is multiplied by P2 is inferior or equal to 2 is multiplied by 2 to the 3. So I'm going to cancel out number 2 from the left and right side. So which means P2 is inferior or equal to 8. Since P2 is a prime, so P2 is taking 3 possibilities. It's taking number 3 or 5 or 7. Okay, you will be in this set 3, 5 or 7. Okay, the minimum value you can take 3, the maximum value you can take is 7. Okay, so this is just base case. By induction hypothesis, let's claim by induction hypothesis P1 is multiplied by P2 and all the way down to the Pn is inferior or equal to 2 to the 2 to the n, like this. Okay, our goal, we are going to prove this product as I run from 1 to the n plus 1 of Pi is inferior or equal to 2 to the 2 to the n plus 1, like this. This is our main goal. Okay, if we prove this one, we done the whole thing. Okay, next step, I'm going to define another sequence. Let's set Q equals P1 is multiplied by P2 is multiplied by P3 and all the way down to the Pn minus number 1, like this. Okay, when we have n equals 2, this Q equals P1 is multiplied by P2 minus number 1, like this. Okay, if I'm going to use the minimum value of P2 here, is giving us P1 is multiplied by P2, which is 2, is multiplied by 3, which is 6. 6 minus 1 is 5, which means Q must be superior or equal to 5, like this, because I'm using the number 3 as a minimum value. So Q must be superior or equal to 5. I'm going to find another prime number. Let P be a prime number such that P divides Q. Okay, we know Q equals this sequence, which is P1, P2 and all the way down to the Pn minus number 1. Okay, so according to the divisibility statement, we have Q equals M is multiplied by P. What is the M? Is a sum natural numbers, like this. Okay, our goal, we are going to find the position of P. Where is the P? We know P is a prime. We know this family P1 through Pn but we don't know P. Where is that P is? We are going to find a new prime. We are going to make sure, we are going to prove this P is belongs to the same family or is out of this family, okay? Or where we know P divide Q, okay? What's the reason we are taking Q equals this product minus 1, which means P, it could be in this group, okay? We didn't say this product P1 through P sub n plus number 1. If we say that, which means is automatically we are outside of this group, okay? So I'm going to prove this P is out of this group. Let's claim P1 different than P2 is different than P3 and all the way down is different than Pn. Also, I'm going to assume all these numbers are different than P. We know P1 through Pn, but we don't know P, okay? Because we have an increasing sequence. P1 is inferior equals to the P2, strictly inferior to P3, and so on and so forth until you get the last prime, P sub Pn, okay? So by assumption, we are going to find the position of P. P maybe is belongs to this family of prime numbers or not belongs to this family of numbers, which is out of this group, okay? We have this relationship between Q and P. I'm simply going to take these values, this product, and replace it into Q to see what's given us. So we'll have Q, which will be replaced with this one. We'll have P1 is multiplied by P2 and all the way down to the Pn minus 1 equals MP. I'm simply going to move over this value MP to the left and minus 1 to the right. So which means I will have P1 is multiplied by P2 and all the way down to the Pn minus MP, as I'm taking this one to the left side of this equation, equals number 1. So I'm going, let's set this one equals a capital A. What's this one is telling us? This one is verifying the Bayesian theorem, okay? Because we know GCD of P and capital A equals 1, because P not divide capital A by assumption, okay? Be careful, by assumption, okay? P is defined as a prime number not belongs to this group, which means not divisible by this product, okay? So this one equals GCD of P and capital A. Since this expression is representing the Bayesian theorem with M is a natural number, so P not divide this product by assumption. If P divides this prime, which means P must be equals one of these numbers, okay? For instance, if we have this product P1 is multiplied by P2 and all the way down to the Pn is divisible by P, P must equals one of these prime numbers, okay? It could be P1, P2 or P sub n, but by assumption, we have assumed by assumption P not equal to any of these primes, which means P not divides this product, okay? Which means is verifying the Bayesian theorem, GCD of P and this product equals 1, okay? Our assumptions was true. Since we have an increasing sequence, we know P1 is strictly inferior than P2, is strictly inferior than P3, and all the way down to the Pn. The Pn is strictly inferior than Pn plus 1 as an increasing sequence, which means Pn plus 1 is inferior or equal to P. Which means since Pn is strictly inferior than P, by assumption, by this proof, which means the minimum value P can take is a Pn plus 1. It could be Pn plus 2 and so on and so forth. We don't know. But it's possible P can take Pn plus 1, okay? So I'm going to use this fact to build our proof, okay? So I'm going to erase this board and move on to the next step. The most important thing that I'm going to use here. So we know Pn plus 1 is inferior or equal to P. We know P is strictly inferior than Q. We know Q equals P1 is multiplied by p2 and all the way down to the pn minus 1, like this. Okay, we know this product is inferior equal to this one, is inferior equal to 2 to the n minus 1. We know this term is strictly inferior than 2 to the n, like this. Okay, so I know two things here. I know pn plus 1 is strictly inferior than 2 to the n. I know this product p1 through p sub n is inferior or equal to 2 to the n by assumption, because we are using the induction hypothesis. Both things, what I'm going to do now, I'm simply going to make this product by multiplying this product by pn plus 1, by joining this one to this one. Okay, so I will have p1 is multiplied by p2 and all the way down to the pn is multiplied by pn plus 1 is strictly inferior than 2 to the n is multiplied by 2 to the n. This one is giving us 2 to the n square, which is 2 to the n square, which is giving us 2 is multiplied by 2 to the n. This one equals 2 to the n plus 1. Okay, this product which I was looking for, so we'll have this product as I run from 1 to the n plus 1 of pi is strictly inferior than 2 to the n plus 1. Therefore p1 is multiplied by p2 and all the way down to the pn. So this is the end of this proof. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you next video. Bye.